Okay, we're group A16 for H203, and for our second project we're going to be talking about sets, unions, and intersections. I'm Steve.
I'm Robbie.
I'm Eric. Nice to meet you.
And there's our artist depiction of Paul on the screen there, who's our scriptwriter. Okay, let's go ahead and move on into things. Now, just a couple of definitions. Unions and intersections. Okay, so suppose we have two sets, sets A and sets B, which are contained within the universe. The universe is indicated by the box, and we're going to be calling that B. Or, I'm sorry, V. Now, the union of these sets A and B can be figured out by drawing lines. So we're going to start off by drawing vertical blue lines in A, and then draw some horizontal red lines in B. Now we can define both the union and the intersection using these lines. So, the union is any area which is affected by colored ink, essentially. So any area that's colored in either blue or red is the union. I'm going to indicate that by circling this area here. That is the union of A and B. Now, the intersection of A and B is the area that's affected by both the colors red and blue. And I'm going to indicate that with this purple line here. And that's the intersection of A and B. We can use these definitions to create some identity laws. So with the union of the empty set simply equals A. We can develop an empty set, which is essentially just a point on our Venn diagram that doesn't really represent. It represents a set, but doesn't have any elements in it, so it's infinitely small. Now it's pretty clear that the union of both A and this point, we can use our same method to color in the set. There's our colored in A. And because we can't color in the point, the union of those two sets is simply A. You can also use this logic to indicate that the intersection of A and the universe is A. We can see that if we color in the universe with red lines, you see that clearly the intersecting section between these two is just the set A. So those are our basic identity laws, which we can use to build on. Now the domination laws, we have our same sets that we've been using. So we have the universe and we have A. And now the domination laws state that the intersection, the union of these two is the universe. And so we can see that even before I color it in, as you're coloring in the universe, everything is covered in here. And so taking the union of everything that exists and the union of a smaller set, A, which we're going to color in with blue like usual, you can see that the union is simply V, the entire rectangle. And so the union is simply the universe. The intersection, it kind of follows conversely that the intersection of A and the empty set, which again we can demarcate by a little point here, is the empty set, because clearly these two sets here do not intersect and there's no overlapping bounds. If we were to say color the intersection, or color the empty set in with green, there would be no green and blue intersections here. Now complementation is kind of another interesting law. The complement of A, which is denoted by this, means anything that's not A. So essentially that can be demarcated in green here. It's anything that's inside the universe but not inside A. So that's going to be your complement of A, not A essentially. And our complementation law tells us that not A simply equals A. So intuitively you can kind of think about this as anything that's not part of not A is going to be A. And so anything that's not shaded in green is therefore going to be in this circle, which as we know is simply A. So that works out pretty intuitively. Now the last basic law here is the distributive law. Now this just shows that we can kind of distribute the notation just like we do in mathematical formula. So if we write down our indications of the sets here, A, B, C, A, B, C, and using the formula on the left, coloring in our sets here, so we have A, you show that A, the union of the intersection of A with the I'm sorry, the union of A with the intersection of B and C is simply equal to the intersection of A union B and A union C. So we can kind of draw this out. This first one is going to be represented in this top line here. So the intersection of B and C, which we can do by our drawing technique here. So this is B, and then we're going to put C in green here. So we can easily see that the intersection is the area between that's shaded in both red and green right now. Now you can see that, and then the union of that set with A. So we can actually market that set right now. That's this set right here is the intersection of B and C, and now the union of that set with A, which we're going to color in blue, is just going to be this area. So anything within these that's defined in the dashed purple is going to be this law. And now you can prove that it's the same thing by kind of doing a similar thing down here. So you're just going to get your A union B, which we're just going to go ahead and draw with blue lines here. This is anything that's inside either A or B. And then your A union C, which we can actually just do with horizontal blue lines. And then you're going to do the intersection of those two sets. So anywhere where you see cross-hashing of lines, you're going to get essentially, we can mark it out with the purple again. You're going to get this area all the way around here, right up there. And you can easily see by the shape that those are equivalent statements. Now Robbie's going to talk about De Morgan's laws.
Hey everybody! Well, as we can see that De Morgan's law is the complement of A intersection of B, and that is equal to the complement of A and the union of the complement of B. We can show this by having a complement of the intersection be shown with vertical lines going everywhere, except for the intersection between A and B. Now we can show that these statements are equivalent by using the red here to do the complement of A and the complement of B with these lines here. As we can see, both statements are equal, as in they include all the universe except for the intersection of A and B. Now, absorption laws are A in the union of the intersection of A and B, and A in the intersection of A union B, and they're both equal to A, which we can show with A being shaded in vertical blue lines, and the intersection of A and B in horizontal red lines here, and as we can see, that's all of A. Now we can also show that the other statement is true by doing A in vertical blue lines again and having it be the intersection of the union of A and B with the horizontal red lines here. And as we can see, the only place where they intersect is in set A. Now the last law I'm going to talk about is complement laws, where A in the union of the complement of A is equal to universe denoted by V, and the A intersection of the complement of A is equal to the empty set. Now we can show the complement of A with horizontal blue lines. And we can show A being with vertical red lines. As you can see, when we take the union of these, we get the entire universe. And when we take the intersection of these, we get ourselves an empty set. Now Eric's going to talk about generalized unions and intersections.
Cool. Back to me again. So, generalized union and intersection. First, I'll introduce union. Generalized union, so first, A1 or A2 or goes on to AN is denoted as U equals I equals 1 until N, AN. So this means that this is a union of collection of sets. And what does that mean? I'll give you a really straightforward example. So imagine this is me, and I have some friends called A1, they have spiky hairs. I have some friends called A2, they have open mouths. And they don't know each other, but I know them. So, if we do generalized union, then it will be all of us. Now, what can this thing do? Basically, with this notation, we could go to I equals 1 and to infinity AI. So what does this mean? This means that, let's take myself as an example again. This is me. And I have set friend A1 with spiky hairs, and then A2 with open mouths, and a lot more friends with special. They all know me, but they. So now it means the generalized union will be all of us. This includes all of us. Alright, now I'm going to talk about intersection. So first, intersection is just denoted as A1 and A2 and goes on to AN equals 2 and I equals 1 and A. So this is, again, my example. This is me and my spiky head friends and friends with mouth open. They all know me, but they don't know each other. So this intersection will represent just me. Now let's expand it. I equals 1 to infinity. Infinity in this case means all of my friends. So I actually have several different group of friends, and since it's till infinity, it means all of us. Now, if we do generalized intersection, they are all friends with me and only me. So this is the result. Just me. Okay, I guess this is the end of the lecture for today. Have a great day. I hope you learned a lot. Thank you.